Hello, everyone, and welcome to another talk at the IMO. And today we are glad to have with us Nikolay Andreev, who is the head of lab popularization and propaganda of mathematics at Steklov Mathematical Institute of the Russian Academy of Sciences. And he's also the brain of the Mathematical Etudes project, and he takes special interest in visual perception of maths. So today, that's what he'll be talking about, mathematics and perception. And if you have any questions, feel free to put them in the chat. And if Nicola prefers, you can unmute yourself and ask it. On that note, thank you very much for being with us here today. Over to you.
Thank you. Welcome to Steklov Mathematical Institute. It's the center of mathematics in Russia. It's not so big institute, something about 100 people. And now we're in the laboratory of popularization and propaganda of mathematics. Here is also my friend and colleague Denis Gradkov, who will help me with and assist me during this lecture. Sorry for my bad English, it's one of the aims to help for him. And these Olympiads should be held in St. Petersburg. And all mathematicians in St. Petersburg started, mathematical school of St. Petersburg started with Parth Shimpi. And here you can see the cupboard from the cabinets of Parth Shimpi. Parth Shimpi proved many theorems, for example, in probability theory, for example, in number theory, and he began the approximation theory when you want to when you want to send the signal for the Sputnik, for example, it is what are the ways to send this signal? One of the way, if you have some signal, you can approximate, for example, with polynomial on some segments, yes, and then you can send only the coefficients of this polynomial, and they shall have the your signal. And here is the beginning of the here on the top is the footstepping mechanism. The first footstepping mechanism is which is the beginning. I shall not take it from the cupboard. All others I shall show you on the table, but this I shall show you in the animation. And so we shall speak some minutes about linkage. Do you know? I shall sometimes show video. Do you know how this mechanism is working? Why they always are parallel? Why they are so? For example, if I shall show you some small parts from our Soviet film. Can wipers work by this way? I shall stop this film, and indeed, you know that of course no, because the system is the next one. The motor is working in one direction, and some linkage раздает. distributes the motion to the y-path. So Chebyshev became to the linkage from the problem of James Watt. I shall show you a small parts of Watt mechanism, and the problem was that this I don't know if the mouse is it's shown, yeah. This point is going on the circle, by the circle, yeah. And if you want to a good work of this mechanism, here must be the straight line. How to transmit the movement, circle motion, yes, to the straight line. From this problem, Chebyshev began to work on linkage, and he made the first full footstepping mechanism. I shall now show it to you. Here, if you want, you then can go to the site Mechanisms by Chebyshev. Here is English version, and I shall show you plantigrade mechanism. It was named footstepping because that's on foot going, and this is the lambda mechanism because it's very similar to Greek letter lambda. Yes, one point is going by the circle, and the other point here is not the line, but the best approximation to the line. And Chebyshev approximated the length of mechanism, so here must be the line. And what's in your mind this picture, this shape?
What does it look like?
What does it look like? Yes, the shape. If somebody is listening now, us. Indeed, Chebyshev thought that this is the shape of the foot of the horse, for example. Here is, we shall take two such mechanisms, and then to another, the similar mechanisms. Indeed, we shall make from these mechanisms one system, and here is the kinematic scheme. And Chebyshev was the professor of St. Petersburg University. He was born in Kaluga. He learned in Moscow State University, and then go to St. Petersburg, and was working all his life as a professor of St. Petersburg University. He have money, and he made his mechanisms very beautiful. You can see how it is working. It was exponated on the International Fair in Paris in 1878, and it was the first footstepping mechanism which was working. And from this mechanism, it's the beginning of robotics. It's the beginning of approximation theory in mathematics. Okay, here you can see many mechanisms of Chebyshev. How they are working, you can look on the site. And we shall go to our models, which are put it here. But maybe before.
What are you doing, huh? This clog?
What is the question? But before we shall show models, maybe you can say one another family name of Russian mathematics, which is well known in the whole world. Do you know? Maybe in chat, maybe by goals.
Just voicing.
Just voicing, yeah. Do you know somebody? I think you know Euler. Of course, Euler. He was he was living in St. Petersburg. Yes, Euler is very great. Vladimir Igorevich Arnold. Somebody say there is a very interesting book of Vladimir Igorevich. Mathematical understanding of nature, but I mean some mathematician of the times of Chebyshev also. It is also very famous. I mean Lobachevsky. Yes, and the geometry of Lobachevsky, non-Euclidean geometry, it is very famous. I shall show you one model which Lobachevsky didn't know, but it's using his geometry. Here, I shall sometimes camera by this way. Here is the surface of constant curvature. No, you know, of course, plane. Yes, it's the constant curvature. And for example, you can translate this paper on the plan, and it's also is in the plan. Yes. No, the same constant curvature. For example, cylinder. Yeah. Cylinder or conic. Yeah. Or cone. Yes. And of course, you know the surface of positive constant curvature is sphere, yeah? And if you shall take a cap on the sphere, you can rotate it, you can move it as you want. Here is the Beltrami surface. Here is the Beltrami surface. And this is the negative negative width. I have I have a metal which have the same constant, the same curvature. Of course, I can rotate it. Yes, it's very simply. Of course, I can use. I can do this way, and always it will really good to be near my surface line on the surface. Yes. But as a sphere, I can rotate I can rotate cap near its center. I can rotate here also. I shall show you. I can rotate, and always it will be near line on my surface because this is the constant with constant curvature. As we know, the Gauss curvature is the the Gauss curvature is the multiplication of two curvatures, yes, plane, and here they are different, but the multiplication is constant. So this is Beltrami surface. Yeah. Okay. We shall go to the other models, and I shall take. I shall ask Denis to put me one of our models. Do you know how the train is going by the tunnel? You see, here is the radius of this path is bigger than the radius of this path, and that is why this path is bigger than this one. And you have no differentials. If you take standard cylindrical wheels without differential, nothing will work. Let us see. Yes. How to solve this problem? How we can solve this problem? What are the ideas? No, indeed, in our life, we're solving independent wheels. No, in the whole world, there are no independent wheels, but one construction, which is italic construction of Italian construction of the wagon wheels. But in all other the world,
the second possibility, tilt the tracks.
no, you can't do this because, of course, it's tilt, but always you shall have the different radius, the different length of path. No, I shall show you the solution. Here is the solution. I have also no differential, but the wheels are conic. Let us see what has happened. I shall put it. What is happening? I shall stop them here. You see yeah, так плохо будет. You can see that's смещается. День смещается. It is shifts, and the radius of inner and the radius of outer wheels are different. That is why when they rotate with the same speed, they go different path. And this idea is working on all the trains. Okay, and where in your life conics are? Where in your life conics встречаются? Where do you meet conics shapes? I shall go for the next model, and you are thinking and writing in the chat. Okay, what are the answers? You can use microphones, not only chat. I shall show you. This is a plastic cup. Yeah. Why it is conic? Let us think about metal with metal bucket. Yeah. How to make it? From the lists from the sheet of paper or metal, you, as we say, you can do cylinder, or you can do conic. Why conic is better than cylinder? It is very, very important. why we're using conic but not cylindric cups. Can somebody say? No, not the weight distribution. Another ideas? Also no part.
Could you precise, please? I'm not sure. To stack them.
Yeah. So it was slave, yeah? Freddy. Yes, to stack its one in another. This is simple geometrical idea, but if you shall use cylinder, you shall transport all separately, and if you shall use conic, you can transport it better. It's one more idea in plastic cup. You know that the conic is the conic is can be bent, yes. You can do this way or this way, and it's the same surface. But this cup is rather rigid. Why? Why it's rigid?
There's an answer.
What's base?
Base.
No, if I shall fix this base, it will not be rigid. It will not be rigid. I shall do this way. I shall show you that with the same base, it will not be rigid. The base is the same, but it's not rigid. Yeah. Why this plastic cup? Inside is rigid because of the because of this edge, yeah. And what must be the surface of the edge to be rigid? It's also a mathematical problem. For example, if you take a small part, even a small part of torus, which consists the circle on which torus is lying on the plane, then it will be rigid surface. And you know, this is working in plastic cups, in aluminium in aluminium banks for the for Coca-Cola, for example, or something like this, yeah. And as we speak about rigid and bendable surfaces, I shall speak about the bendable polytopes. Yes, I shall take constructor.
A child constructor.
Yes, a child constructor. I shall take it. If I take the triangle, with fixed length of sides, it is rigid, yeah. But if I take the foregone, for example, I shall do it here. I'll do it here. It's not rigid, yeah. If there are or there are no rigid polytopes.
So the question is, are there rigid polytopes that would be
Yes.
rigid in the same way as the triangle is?
Any convex is not rigid and not flexible. It's not rigid, flexible maybe better. Any convex polytope is not flexible. But if there are some flexible polytopes, indeed there are.
Most simple.
And the most simple now in the camera, it have now 9 vertices, and it's rigid.
Yeah.
It's flexible. Yes, it's flexible. Here you can see all these models. You can see on the side mathematical etudes. I shall maybe show. That is why now you are only listening, and then you can read the text which you can find there. It is. You can find there the films. For example, if we shall speak about flexible polytopes. The translation will soon. The translation will soon be here. Yes, and maybe I shall show you in Russian some pictures. Here, maybe I shall show you only pictures. For example, what we were speaking about polygons, and because the triangle is rigid, non-flexible, you have the Geron formula for the triangle. And so for other polygons, you shall now have Geron formula. And here is the net of this polytope which I showed to you. You can make it by your hands. And the question was and the question was if the volume when it's flexible, if the volume is changing or not. What do you think? When I do this way, the volume is changing or not? Yes, all faces are rigid and not
changing.
Not changing. Yes. What you are thinking about the volume? The volume is not changing. Yes, it's constant, and it was solved. It was proved not so far ago in 19th of the 20th century. And then we shall go to another models, and as we began to speak about conics, maybe.
Wait, so the volume is constant for all polytopes or only this one?
For all flexible polytopes. Indeed, it's the analog of Geron formula. That's the volume is the yes, the volume is the roots of some polynomial where the coefficients are the functions of the length of edges. Because the edges are not changing, then the polynomial is not changing, and you have discrete sets of roots. You understand that if I shall small, a little bit flexible, it will be it can't change, the volume can't change much. That is why it's also standing in one root of this polynomial. So the volume is not changing. Okay, we started with conics. One question for international very strong mathematicians. Yes, here is the circle. Here is the ellipse. Where is hyperbola and parabola? Hyperbola or parabola? Here, no, for example, let's speak about parabola. This one or this one? This is parabola or not? Yes. Yes, this is parabola because as it's
It was mentioned.
mentioned, yes, it's parallel to the it's parallel to this line, and it will not intersect the second half of the conic. But the conic must
Think about
about in sides from the depth, yes? That is why this plane will intersect and this half, and this half will intersect only one. So here is this one is parabola, this one is hyperbola. Let's start with hyperbola. I have hyperbola here, and I can make such exponent because when I rotating when I rotating the line, I have hyperbolic surface, and in each points of this surface there are two lines from this and from second families. I shall show it to you. You can take the cylinder, and if you rotate one circle, you shall have this family. If you shall rotate in another direction, you shall have this family. It was the great engineer Vladimir Shukhov in Russia, which began to make some towers on this idea. I shall show what you can make by I take sticks, and you can make this by your hands. Any point, you have this family and this family. Yeah. This idea is very, very good. I shall show you one picture. I shall show you the one picture of very famous tower. Which is standing in Moscow. This is the first project of the Shukhov Tower in Moscow. In Moscow now are standing smaller. But if this project was to be constructed, you see how the idea of hyperbolic towers is working. It is bigger than Eiffel Tower, but 4 times lighter, yes, than Eiffel Town. How to do this? You can see on mathematical etudes. I shall not speak about it, but at the last, I shall. Well, I'll go into the next exponent. Exhibit, yes. Okay. Here is I shall make, of course, you know how to make the ellipse, yeah? I have 2 points. I have yes, and here is the ellipse, yeah? Here is the ellipse. Of course, you all know how to do by this way. What I shall do, I shall take this ellipse as a beginning, and I shall take a bigger row. And do the same algorithm. What line I have? No, not circle. You can see this is not circle. It's not a projective projection. It's not a circle. Another ellipse. Yes, it's true. What are the focuses of the second ellipse? What are the focuses? The same. Yeah. It's it's the ellipse with the same focuses, confocal. And if we use these words, what's mean the word focus, from what language, and what it's mean? What go to Google, yeah? It's from what? It's yes, the focuses are the same. It's mean очаг огонь. Fire. The words focus mean fire from the Arabic. Why? Because and parabola and ellipse and hyperbola have optical properties. For example, if you in one focus puts the I shall maybe show. I shall maybe show. I shall. We have a very interesting book. It's in Russian. That is why I will show only pictures from its. So here is the optical property of ellipse, and can you formulate it? Maybe I shall show one more of these pictures. Can you formulate somebody? That's if you shall start, the light shall start from the one focus, then after the reflection, it will go to another focus. But this is only the half of the optical property. The second half is that they will go simultaneously. Yeah. Why? Because the path of any light's way is this this rope. Yes, for this point is this rope. For this point is this rope. So it's and the rope was the same. Yes, it's the same. Okay. Can you prove this theorem? That's by this way we shall have the ellipse. We shall have the ellipse with the same focuses. Indeed, there are no elementary geometrical proof because mathematicians now know only the proof which use limits, which use derivatives, but there are no it's still known elementary proof. Why? Because how this rope what is the mechanism of this rope? You see, you have two lines, tangents. Yes, you have two lines, and you have an arc of ellipse, and the arc of ellipse is very, very difficult, very, very complex, even to calculate the length of ellipse. The mathematicians using the elliptical integrals. Yeah, so that is why there are no elementary proof. Okay, and maybe we shall show you. Maybe we shall show you one more exponent, not to not to offend parabola. Yes, we shall show you one more exponent. With Denis, we shall now take it. Here is something like parabola. Yeah, here is focus. And this Gorka, this ramp is making that the ball will go parallel to the axis. Yes. What it will be? Okay. Let's go to the focus. If I put it in another, it's also go to the focus. Yeah. I can put this side, and it's also go to the focus. The question. The question: where here is parabola? Where is parabola? This one, maybe some else. Is the parabola is the wall Champing? It's not the truth. I shall put it. We shall put the exponent here, and you are thinking this moment. So where's parabola? When the ball is rotating, yeah, by what point is rotating the ball? By the center, yeah. That is why you must have the equidistant equidistant curve on the radius of the using ball. So the mechanic is very, the mechanic is no, maybe better than, it's bigger than mathematics. You are not to know all mathematical apparatus and to have some mechanical understanding of life. The mechanic is very interesting. And to prove it, I shall show you one more exponent, which maybe you know well, Celtic stone, yeah? If I shall rotate it in one direction, it will rotate. If I shall rotate in another direction, it will not rotate. It's Celtic stone. No, maybe some small explanation. Some small explanation. This will such mechanism will rotate this direction and will rotate this direction. Yes, I shall do something with its mass. So here, this way. Yeah. And let us try. This direction is good. This direction is not working. Yeah. Who wants to understand can in the internet find Celtic stone. And one another mechanical exponent. If there are in India such toy, if it is with the sound, why this toy have always one stable point? Why it's have one stable point? I can do this way, but it's always go to this point. Where it's at the bottom, yes. I shall break it, yes. Here is this way, and here is the weight in the bottom, yeah. It's the weight in the bottom. Yes. The question of Vladimir Igorevich Arnold was if there are homogeneous bodies with one stable point. If there are homogeneous bodies with one stable point, I shall show it, the answer. The Hungarians proved find the solution, and the name is Gambach. Here is the body. I shall and what way I the name is Gambach. С двумя точками над «о». Okay, this was these were some exponents, and maybe I don't know, Parth, how it's better to show more exponents or to answer the questions.
I think it would be better if we just look at more exponents.
I think also, yes. I can show you for till tomorrow closing ceremony. There are many. Maybe I shall now show you one exponent, and it will be the problem. I shall ask the question and have 2 minutes. Here is 40 circles, yeah. Here is 40 circles. Can you or not put one more circle here? Can you or not? Maybe I shall ask Denise to assistance. You can say what to do to him. Come here.
Yeah, the answer is already.
Yes. Ну, давай продемонстрируй.
Okay.
Значит, вдоль короткой стороны. В руку не бери, нехорошо. То может в руках петь.
Yeah. So am I doing what Fred is suggesting? Right, so I believe that we're using the hexagon tile, right? So if you take all the centers of the discs, you get hexagon tiling of and even each second row or column from your side of view, each second column is contains one less ball. The fact that their width is reduced. I did not do it the right way because I began with a short one, so everything. And now I have enough place for the last one. I even had some extra space. It is known that such a tiling, in terms of if you are trying to discs on the plane to fit given surface area, then others obtained with hexagonal.
Dennis, can you? We can't really hear you from there.
Can't hear you from me?
Let me perhaps. I'm not sure where the microphone is right now.
We can hear you now.
hear me.
Yeah.
Okay, nice. Because I don't know where the microphone here is.
Okay.
So there is a
no, you might want to stand up. If we can't hear you sitting.
It's all. Okay. Do you
yeah.
hear me now?
Yes.
Okay, nice. So there is a very interesting generalization of this problem, which is sphere packing in general dimension. On the plane, you see that this is the optimal one. But what happens if you take spheres in 3 dimensions, for example, or spheres in 4 dimensions? This gets very difficult very quickly.
Yes, and in the on the results of Maria, you speaking on that.
So I only told that there is a generalization
Yes.
for 5 dimensions.
And for 8 dimension and for 24 dimension, it was not so long ago, some years ago, the best density packing was proved by it was proved only a few years ago about this. Okay, and we shall now go. And all these are very applied topics. For example, when we were using modems, for the internet, to connect to the internet, then we were using the codes in 8-dimension our Euclidean space, the codes on 7-dimensional space. I want to show you one more exponent. What is the biggest achievement of Archimedes? We know this because Archimedes himself on his tomb said to draw some picture. What was the picture? What he mentioned, what he thought the biggest his achievement? Maybe somebody in chat. Not surface area, but the volume of the sphere, the volume of the sphere. And here you can see the the weights of Archimedes. Here is the cylinder. Yeah. Here is the cylinder. Here is the conic, the cone. Yes, by the same radius and the same height. And here is the half of the ball of the same radius. Yeah, and the scale is equalized. Yeah, the scale is equalized. It's very interesting that it will be in the equalized position, not only when I take all, when I take all these bodies, but their parts. I shall take one here. And one here, and all equilibrium. Yeah. Let's try one more. This one. This one. This is not the equilibrium, yes, but I take this one and again the equilibrium. Why? Because the section which is parallel to the plane in this section, this area is equal to sum of these areas. This is the Cavalieri, yes, Cavalieri principle. Some ages before the Cavalieri, yeah, in the times of Archimedes. Yes, Cavalieri principle. It's working. All of us can prove this. But I shall put them all back, yes, and I shall say a few words more. You see, here is something straight, yes, no lines, yeah. Here is also some lines, and here you have very difficult surface, and there the equilibrium is working. It's something unreal. No, unreal. This is very, I think, good. And then we shall take another exponent. And maybe we shall go to very, very primitive thing, which of course you know, Pythagorean Theorem. Yes, geometrical view, that's the area of this square is equal to the area of these two squares. Yes, and Pythagorean and the theorem of Pythagorean says that if you have two two polygons on the plan with equal areas, then they are made of same parts. Yes, you can cut one of polygon here, this one, on the parts from which you can make this polygon. This is Pythagorean theorem, and indeed for this construction of Pythagorean theorem, you can use 5 parts. This is the smallest. I shall show you. I can put here. I can put here. No, okay. Often I didn't give the solution, but maybe to you I shall give it this way, this way, this way, and this way. So the same area, the Fagorian theorem is working. Yeah? But the most famous illustration of Pythagorean theorem is due to the dissection. I shall show it to you. I take square. It's very famous dissection of duodeny. I take square, and then I shall have a regular triangle. What is the difference between these two exponents models? Yeah, here is hinged continuously. I'm making this, yes, and here to put them some way and so on. The theorem which was proved in the 21st century, that's any dissection you can make by the hinged variant, by such idea, but the number of parts will be very big. Indeed, mathematicians don't have good estimates for the number of parts. But in these two models, which I show to you, this is the smallest number of parts. Here 4, yes. No, in Pythagorean theorem 5. How to find such dissections? You can again. I shall send you to the mathematical etudes. There are such film there. Okay, and we shall go to the exponents. Maybe to continue and to end the theme of dissections. Indeed, always when we can find area, we are using dissections and Pythagorean theorems. This is example for parallelogram. Yeah, this is example for. This is the example for trapezium. Yeah. And you have here two parallel equal lines, segments, yeah? Where in algebra, not in geometry, you are using two parallel equal segments. In algebra. Equal sign, yes. Equal sign. How old it is? How many years ago? And who invented equal sign? The author wrote what can be more equal than two equal parallel segments? And he will introduce this equal sign, yes, more than 400 years ago. No. Who interested can find this in internet, maybe. Okay, and I shall show you one more very simple model to you. Yeah, how to calculate the area of the circle. I can do this way. And for Indian mathematicians in many years ago, this picture was the proof. They wrote, look. They wrote look here, and this was the proof for Indians in ancient times. Of course, now it's not the proof. I shall not show you the proof, but I shall do this way. I shall do this way. And I have a rectangle. No, the approximation of the approximation to a rectangle. Yes. Here is the radius. Here is the radius. Here, half of the circle. Yes, half of the circle. And here is PR. Here is R. PR square. Yes. Of course, this is not the line. But if you shall take bigger number of parts, it dissects in smaller spots, then it will be much closer to the circle. One more very famous model. I have two equal parts. Yes. What do you think I can make from these parts? The parts are equal. Yeah. No, many people do this way, and I don't know such a figure. But if you rotate, you shall have a tetrahedron. Yeah. What follows from this fact that the tetrahedron have a section square, section. It's very interesting fact. Indeed, if you shall, this section is geodesic to tetrahedron. If you shall take rubber, if you shall take a rubber, this will and put it on this section, it will not go anyway. It will be stable. This in mathematics we say geodesic. Yeah, I shall show you one geodesic on another platonic solid, but only one. Here, of course, there are many geodesics. You can, for example, look for the paper of Volodya Protasov, who finds all geodesics on the tetrahedron, and I shall show you another polyhedron. I have two equal shapes made from carton. 6 5-gons radial, yes. there are two shapes. Indeed, найди тоже кинь, там есть в английской версии сюда. What shall I do в моделях? I shall do this way, rotate one to another, and I shall take a rubber and do this way. Here, here, here. Understandable? If I shall through it, I shall have the dodecahedron. Yeah, I shall have the dodecahedron. And here is also geodesic. You can prove that this angle and this angle are equal, and that is why it is geodesic. There are not only such geodesical lines on the dodecahedron, but each of you can make such model. Yeah. I shall remember you the Steingau's book, Mathematical Kaleidoscope. Great book. The idea of such model was printed in this book. Maybe the last exponent I shall show to you. What is it's the name is anamorphic, yeah. We shall see the отражение, reflection in cylinder, yeah. Indeed, it is inversion on the line center of the cylinder and the наблюдатель, observer. It is inversion. We know that inversion transform circles to the lines. Yeah, no, circles which are going through the center of inversion. No, one more picture. Maybe this one. Yeah, sure. And I show you this exponent to mention one my friend and colleague, very good popularizer of mathematics, and I strongly recommend you to look to his lecture, Tadashi Takieda. And when we meet with him on the Congress, he asked me if I can make a cat. I said no, and he take a small sheet of paper, this one, pointed 3 segments. Yes, let's see. It's a cat. I don't know if you see this. Tadashi is very great, and his lecture you can find in internet, and you shall have огромное удовольствие. A huge pleasure if you shall listen to him. Okay, indeed I can show you exponents to the closing ceremony. We shall not do this way. Maybe some questions.
So how do you recommend that we think more visually when we are doing maths usually?
When we shall translate our book, to read our book. But now it's only in Russian. Indeed, very soon. It will be the new design of mathematical etudes, and you know that in 2022 it must be the mathematical congress at St. Petersburg. Yes, it is now a tradition that at first the mathematical Olympiad and then mathematical congress. Yes, and till 22 we shall in the section models we shall gather all exponents which which are known in the whole world, which we invented. In this section, it's about 400 exponents. So you shall have a big field to look, to explore. Yeah.
So there's a question in the chat.
One moment. Maybe I shall show you the linkage, which translates in the circle movement to straight line. Two authors, the Pythagorean, French engineer and French engineer and mathematician, and the students of Chebyshev, Lippmann, Lipkin. Chebyshev, we started with Chebyshev with St. Petersburg. We're ending with Chebyshev. Chebyshev didn't like complex numbers, and he didn't, as I mentioned at the beginning, he didn't solve the problem to transform circle movements to straight line movements. Yes, but his student made this exponent. Here, these 2 points are inversion. Results of inversion. These 2 points. If you have this length and this length are equal, here is rhombic, you cannot think about this this segment. These points will be always the result of inversion under some circle. Yeah. Right. And then we take these segments, and this will go by the circle going through the inversion center. So this will be the line. This will be the line, straight line. This was once more Lippmann, Lipkin, and Pythagorean invented these exponents. I can show you maybe on the plan. I shall take this one. Not this one. I shall. I shall show you. This is a circle here. Yes. Right. And here is the straight line. Okay. Again, Денис с этюдов там есть. Again, we shall now give you linkage. Нет. Another questions.
There was a question, есть ли значит, влияние, зависимость между этими значит, узнаванием этой красивой математики и результатами на международной олимпиаде?
You see, in Maykop, in Adygea, in Russia, there is a town Maykop, the capital of Adygea. There is a mathematical park where the exponents standing on the streets. You can see these exponents, and some days ago, it was the concert of symphonic orchestra in this mathematical park. And mathematics and music are very beautiful. To see this beauty is maybe the general aim in mathematics. Then, if you shall see the beauty, you can solve your problem. If that is why, of course, there are no such прямой such direct connection between Olympiads, between these exponents, between Olympiads, mathematical, and between mathematics. There are all three different things. But if you can see the beauty, then you can solve the problem.
But then don't you think that is limiting? Because if you rely too much on visual, then you won't be able to do maths about things you can't visualize, like more dimensions?
Если, ну, как бы, мне кажется, я вам что это необходимо ограничивает, потому что если вы только будете визуализировать, вы не сможете развиваться геометрией в этом случае.
I spoke with many mathematicians, and only a few of them working writing formulas. Most of them at first visualizing, чтобы это не значило.
Whatever this means.
Whatever it means, that's the picture maybe, but visualization in the problem in their minds, and then write formulas.
Okay.
And I think that many participants, the most participants, do by the same way.
Right.
And any dimension, and any indeed in algebraic geometry, also visualization in mind and then solving something.
So, are there any more questions?
Как связать, значит, движение по окружности и движение по эллипсу, если устойчивости почти начальной точки?
As I say, I'm not, I have no Olympiad history in my life, and I shall not give a quick answer on this question.
We are speaking about the last question about the relation of motions. I can perhaps answer from my part that the previous models do not give us a direct answer to this question because the ellipses will confocal, as I read. So we cannot derive it directly from the examples we have.
Right. So I would like to ask, what inspired you to start this project of visual models?
No, we have several projects in our laboratory. The first was mathematical etudes. It started in 2002, and it was with 3D graphics, and it became very famous. The first films were on my scientific problems, is Thomson problems and contact number problem. The first two films was on my scientific work, but they became so famous that we started this project and do many films you can find in the internet. The next project, the models. And indeed, even if I take Pythagorean Theorem, if you shall make this puzzle by yourself, then you shall not forget the Fagorian Theorem all your life. Of course, you are not the aim of these models, indeed. This and the many scholars in Russian and not only in Russian can learn many from these models. It is, I don't know how in the countries which participants from, but in many countries in the world, there is a problem that scholars don't like mathematics, don't want to study mathematics in school. And something maybe playing with such models can help them to at first understand some facts, and the second to become to love mathematics, and then it will be formulas and so on.
That's a great answer. So if there are no more questions, okay, there are more questions. How do you get all of these models?
Где или как вы получили
No, we in laboratory of polarization and propaganda mathematics, they are working not only me, and for example, Sergei Konovalov, Nikita Panin, Pavel Kожевников, Roman Koksharov, who are designing and programming our sites, and Mikhail Klinchenko, who are doing 3D films, and Alexander Lishinsky doing these models by its hands, and he's a great master in the wood, and we speaking what to do, and he's doing from the wood. It's very beautiful. I shall show you one thing, maybe. On this exponent, it's the constant width curves, constant width figures. It's made from the red. It's made from the redwood, and here is incrustation of the also by the wood, if different wood. Yes, clone. So, Alexander Lishinsky, our modelist, is very good. You can see that this is wood by the no, by the shade.
Yeah, there's also a question that says, why are water bottles shaped in more than one conics? Is that?
I shall wrote you. I shall maybe draw you one moment. Maybe I shall use our book. It's the picture from our book. I shall find it now. Here it is. Here is the some parts of torus, yeah, and this is the edge of plastic cup, yeah, right. And here you can see two quarters of torus also, but glued not as this way, but this way. And this is the top and the bottom of the aluminum can, because it's also the surface. It's also the surface with the tangent, which is perpendicular to the axis.
Okay.
And this is the direction for the surface to be rigid.
Yeah, so perhaps a variation of the answer would be that some of the geometry of the bottle is just for convenience, and then you are gluing together several conical sections that make it most convenient, and you glue it using those torus shapes.
Okay. So I think it's time to end the session because the results came out a short while ago, and I'm sure the participants are very excited for that as well. But thank you very much, Nikolay. I, for one, enjoyed the talk very much, and it was really fun to look at all the models. And I'll definitely check out the website, as should all of the participants.
I invite you to visit Moscow, our laboratory, and the Russia at home.
Thank you very much. Thank you, everyone, for being here. Thank you, Dennis, for helping out as well.
Thank you.
Great. And all the best to the participants.